Lenz's Law. Lenz's Law is a bit confusing, but we'll be fine. We'll take it bit by bit. So Lenz's Law is that when you induce a current, that current will produce a magnetic field which opposed whatever caused that current. So this definition in the center here is a bit easier to follow. The direction of an induced electric current always opposes the change in the circuit or the magnetic field that produces it. And so remember back here, this is page 215, electromagnetic induction. Remember back here when we went through these diagrams and I said, if I bring a north in here, this will try and repel it, and it does that by generating a magnetic field with a north this end, and to do that the current has to flow in this way. So it's the same idea. It's exactly the same idea. So, and the thing is too to realize if it didn't oppose, so it opposes it, you're having to do work to push the magnet and the solenoid together. That work is converted into electrical energy. If it didn't take any work for you to do that, then you would be producing electrical energy out of thin air without any other energy source. So that would be against the law of conservation of energy. So it actually takes energy for you to push this towards this. All right, so as you push it in, it's going to generate a magnetic field which opposes the motion. So it's going to have a north up here to oppose that north. Right hand solenoid. So north is your thumb. Your fingers would go round the back and up the front of that. So if you want something to hold, right, so that means the current is going to be coming this way, which is what the diagram shows. If you pull the magnet away, you need a south here to oppose that motion. So you have your north at the other end and your fingers are going round the back and up the front. So the current is going to come up and over, up from the back and over in this direction. So that's not anything new. We've already knew that from a little bit earlier. Now, this Lenz's Law is going to, in a minute, morph into one of these right-hand rules. And when I was looking up the difference between why right-hand rules and left-hand rules, right-hand rule is for generators. So that's where you are moving the wire and inducing a current in it. All right, so there's an example here where they're moving a wire in a magnetic field to induce a current. Now remember, the conventional thinking was that the positive charges moved, so it talks about that here. But we know now that it's the negative charges that move. But when we're talking about the direction of current, we're looking at the direction, the positive round to the negative, right? Conventional current. Righto, so there's the Fleming's right-hand rule. We have got our thumb for force, which we had last time. We've got B for boogers and magnetic field, and we're left with I for current, as in I don't care, right? It's got a little memory thing here, FBI. Who could remember that? Mine's much better. You remember it however you like. Okay, let's have a look at this. This looks very complicated, but it's not too bad once you start looking at it. So we've got a nice uniform magnetic field of 0.20 Teslas into the page. That's what the X's indicate. It's going in like an arrow. And sitting on top of that is like a wire loop or metal rails that are going around. And then this piece here is a little metal rod that can be moved backwards and forwards along those rails. So it will conduct a current around in a square. All right. So there's two ways to get a current in here. You can change the magnetic field and that will induce a current which will oppose the change in the field, or you can move the wire so that you are changing the amount of magnetic field that's inside the loop. So the first example is here. Here's the formula, EMF, number of turns per meter, change in the magnetic field and area divided by the time frame that it took to happen. Area is not going to change. We're going to change the magnetic field. So they've brought that forward. And they've gone change in magnetic field, the time that it happened in. Right. One loop, area doesn't change. So it's just 0.2 by 0.2. So that's that. And it goes from 0.2 Teslas down to 0 in 5 milliseconds. So that's down to 0.2 in 5 milliseconds. Down from 0.2 to 0 in 5 milliseconds. And to get rid of the negative, they've used the absolute value of the EMF, which is fine. All right. We want to know the direction of the current. Is it going to go around in a clockwise direction, or will it go in an anti-clockwise? So you actually use your solenoid, right-hand solenoid rule. The direction of the current is going to produce a magnetic field which opposes the change. So we weakened the magnetic field, so we want to strengthen the magnetic field by producing a magnetic field in the same direction. So your thumb would be going into the page, your fingers curl round, so it would go clockwise around that square loop. All right. Second way to do it is by moving this metal rod. So it says it's moved 5 centimeters per second, and the magnetic field is going to stay at its initial value. Right? So it's the same formula, only this time they've brought the magnetic field out and left change in area. So you have to work out that little area and the amount of time that it took place in. So it was per second. So it's going to be 0.010 meters squared in 1 second. Again, they've dropped the negative by using the absolute value. Now, this is the confusing part for this one. When the rod slides to the right, the amount of flux enclosed by the loop increases. The loop opposes this change and generates a field that is in the opposite direction to the existing field to get it back to its original value. All right, so it generates a field in the opposite direction because there's more magnetic flux. So it wants less magnetic flux, if you like. So it's going to produce a current this way. So in this movable rod, it's going to go from B to A. So it's going to go up like that. So that's going to oppose the motion. The other way you can do it is to use Fleming's right-hand generator rule. Right, and it's just the way the page is, it's a bit hard to do, so I'm going to turn it up the other way. All right, so this is our booger finger into the field, into the page. The force on the wire went this way, and the current that produced it went from B to A. So it's a bit tricky because this is a square. So just think about the part that's moved. That's where the current is going to initially come from. So into the page, the motion of the wire was across this direction. So the current in this bit of wire that's moved is going to be from B to A.